This is a production of Cornell University.
So we've talked about these paramaterials. We've talked about the rock types and the sort of sequence of weathering and the surficial processes. Let's actually talk about what those surficial processes are. And we're going to talk basically about the weathering process themselves. We have two types. We have physical weathering, where you're actually banging things together. And we also have chemical weathering. Let's start with the physical weathering. Okay? There's basically 5 different types of physical weathering. Okay? We got freezing and thawing. You can imagine something expands and contracts when it freezes and thaws, things are going to break. Okay? We also have uneven heating. Okay? If I have a big rock and one side I heat and one side stays cold, you can imagine that the hot side is going to expand and the cold side is not. And I'm going to have differential sizes, which will potentially create cracks and fractures. Okay? Next one is abrasion. I'm literally taking a sandpaper to it. Okay? This can be an ice, this could be water, or it could be wind. Next one is shrinking and swelling. Okay? As things get wet and dry, wet and dry, wet and dry. Okay? And then finally, biological stuff, roots themselves. If I have a crack, okay, yes, it probably started from something else first, but I got a crack, a root gets down there. That plant is going to start growing, and that root's going to start expanding. And if it starts expanding, it's going to expand that crack, and the things are going to break. Does that make sense? Okay, so let's give you some examples. You guys see this slide? It's visible, pretty visible. Okay, stream, rather large boulders here. Okay, the boulders are rounded, which is an indication of what? Water tumbling. Okay, if something's rounded, it's been tumbled. Okay, so these boulders, rather large, that tells you that this stream, at some time, if not all the time, every sort of flood, but if not later, or at some time, this stream has produced a lot of water, because you need a lot of water to move those types of boulders. Okay, but as these boulders are moving in the water, they're tumbling, they're smacking up against each other. They're grinding stuff away. You can see these boulders are basically sitting in the product of their grinding away. Okay, this is basically sand with sandstone boulders. Here's another water feature. I have a crack forming, so for whatever reason, water gets down here. It freezes, it expands, it breaks. Okay, produces very distinct scree fields. Has anybody seen these scree fields? Okay, but you're basically looking the angle of repose with these rocks basically from summit all the way down. Okay? Another good example. Okay, this is expansion. Okay, as rocks get exposed, imagine how big this rock is. This is a mountain-sized rock. Okay, so as it comes up and it's exposed to the surface, what's going to happen to it? Well, as it's exposed to the surface, the stuff that's up here doesn't have an overburden on it anymore. The pressure is released. So as a result, if I have something compressing and then I'm releasing the pressure, you can imagine that the stuff at the edges, at the place that the pressure is being released, is going to expand. Okay? And the stuff below it still has pressure on it, so it's not going to expand. And if I have the edges expanding, I'm going to start seeing fractures. Okay? You can start seeing these fractures. Now, that's not to say once I have these fractures, other processes like water is going to get in there. But the initial fracturing is due to this release. Okay? This is a mountain-sized boulder. It's a big rock. You can imagine that the bottom of this rock has got a lot more pressure than the top of the rock. And when it's exposed, you're going to relieve pressure at one point, differential pressure release, and you're going to have fractures. How about something a little bit smaller? Do you see the sort of flaking here? This is heating. The sun is literally shining on it. It's heating up the very surface, the skin. Okay? If it's heating things up, it's going to expand. It's not going to be like this, where it's going in very deep. Okay? It's very much at the surface. Okay? It heats up, and it basically potato chips. It flakes off. Has anybody seen something like that? Oh, I should go back to this one. Has anybody seen something like this? We have it a lot around here. We have a lot of this around here as well. It's just you need to find the exposed points. This is an older landscape from a geologic sense. From a geomorphic sense, it's very young because of glaciation. So let's move on. These are my favorite slides from this lecture. But I mean, you can see this crack right here. I mean, the plant's roots have basically gone down that. And here, I mean, this is basically an Ansel Adams shot. I mean, that tree has basically filled that and it's expanding it. That's a cool shot. I have no idea where I got that one either. But this is physical weathering. The thing is literally being ripped apart. All right. You made it through that one? Let's move on to chemical weathering. There's basically 4 types of chemical weathering. We're going to talk a lot about this later in the semester. So I just wanted to sort of touch on this right now. You have hydrolysis, which is basically an addition of a proton to the structure. This is at the chemical level. I'm taking a proton, I'm adding that proton to the chemical, to the element or the mineral. Okay? I can also have hydration, where instead of a proton, I'm literally adding a water molecule. Okay? I also have oxidation and reduction processes, and we'll talk about this when we start talking about colors. But basically, I'm seeing a gain or loss of an electron. You guys see the trend here. I'm going through proton. I got water, hydrogen, proton, water molecule, electron. Or I can basically have a dissolution carbonation reaction where the molecule is literally dissolving. Okay? In this case, we're looking at proton from carbonic acid. This proton reacts, and basically it's an acid. This is my weak acid in a million years story. Okay? I take that acid and I'm basically just totally weathering something. I'm dissolving it. Okay? One example, this is a hydrolysis example. But basically, I'm looking at a potassium aluminum silicate here. This is the mineral that I start with. My water molecule right here, water disassociates. That's the term for pH. But it disassociates into a proton and a hydroxide. In this case, this proton is going to react with this mineral. And it's basically going to react with that potassium. The proton switches into the potassium's location. The potassium is now in solution, where it can become an element for nutrition, or it can be leached from the system. This is fertility, okay? But the element that we started with, this is now something different. It's been chemically weathered, okay? Weathering doesn't necessarily mean destruction. It could, in fact, be a building up, but we're looking at a destruction of the initial material. Does that make sense to everybody? Down the bottom is basically the balanced equation, but this is the slide that I started today's lecture with. Here's those primary minerals. Some sort of chemical reaction producing these secondary minerals. In this case, I start with a primary mineral up here. I lose the potassium, and I end up with an illite. Okay? Start in here. If I lose a magnesium and I lose a potassium and I gain a water, I'm moving into the vermiculites. Down here, if I'm in the mafic end of the spectrum and I lose a potassium, I'm moving into the clay chlorites. Remember, these primary minerals, these minerals down here are different than those minerals. So even though I'm losing a potassium in both of these cases, I'm producing different secondary minerals. Ultimately, I'm going to have enough weathering of potassium or gain of potassium or loss of magnesium or gain of magnesium that I'm going to move into the smectites, the montmorillonites. I start losing silica, I'm going to start moving into the kaolinites. And if I lose even more silica, I'm basically into the iron and aluminum oxides. Okay? We feel comfortable with this? We will revisit this one. I don't expect you guys to memorize this. Okay? Which brings us right back. Oh, go, question.
The mafic rocks are more chemically reactive. Is that what you said?
The mafic rocks are more chemically reactive. They're sort of at this end of the spectrum, but that's just, having said that, I mean, this stuff is, it is reactive. This just happens to be more reactive. This takes a lot longer than this. Which brings us right back to this slide. Now, does this slide make a little bit more sense? We start with the magma. We have uplifting and igneous rocks. Superficial processes produce sediment. Okay, that sediment or that igneous rock, that sediment material can become soil, but that sediment also can be transported and it can be buried. Okay, in that burial process, if it gets buried deep enough, it can actually be turned into hard rock and becomes a sedimentary rock, which in turn can be weathered. Okay, this material can be subducted, put back down, and it can be heated up. And for whatever reason, if it doesn't go back down to the magma but actually comes back up to the surface, we have this metamorphic material, which in turn can be weathered, produce different soils. But ultimately, all of this stuff will get back down into the magma and we'll start the cycle again. Cool? Questions? Do we feel comfortable with this?
This has been a production of Cornell University, on the web at cornell.edu.